Let u be a differentiable function of x, then the integral of 1 over u du will have the antiderivative natural log absolute value of u plus c. Basically, if you can get an integral in the format of derivative over original, and what I mean by that is if you were to take the derivative of the denominator and you get the numerator, then this antiderivative formula applies, and it's called integration using natural logarithms. Here's a couple of examples where we have the integral of 2 over x dx. Remember, 2 is a constant and can be brought out front, and so that gives us 2 times the integral of 1 over x dx, which is a perfect candidate for natural log integration. So we're going to get 2 natural log of absolute value of x. Remember, natural log is only defined for positives. So if what's in here or in your denominator can be negative, it has to go in absolute value bars plus your constant of integration c. Sometimes this technique requires u substitution, and that's the form that we looked at, or the technique we looked at in the previous video. I'm going to let the denominator be 4x minus 1. Take its derivative, you get 4 dx. Remember, with u sub, after you make a substitution, the derivative of your substitution needs to account for the rest of your problem. Well, 1 dx is the remainder of the problem, and it's equal to 1/4 du. 1/4 du, and then the original part was 1 over u. Well, that's the perfect candidate up here. It matches exactly to have an antiderivative of natural log absolute value of u. 1/4 natural log absolute value of u plus c. And remember, if it's an indefinite integral, you sub back in the original term for u. 1/4 natural log 4x minus 1 plus c. If you have a definite integral, in this next example, we're integrating from 0 to 3, x over x squared plus 1 dx. What I notice is when I look at the denominator, I see that the derivative of x squared plus 1 is 2x dx. Well, that's pretty close to this numerator. If you divide both sides by 2, then you have x dx isolated, which this can be swapped with 1/2 du. 1/2 du. The original fraction in the problem becomes 1 over u. If you have a definite integral, the original upper and lower limits are assigned to the original variable. Since we switch from x to u, we have to adjust those. Top limit 3 squared plus 1 gives us 10. Bottom limit 0 squared plus 1, that's 1. So these are our new upper and lower limits, so that's where I've adjusted with 1 and 10 here. Take the antiderivative, you get 1/2 natural log absolute value of u evaluated at 10 and 1. So that's 1/2 natural log of 10. Since 10's positive, you don't have to put it in the absolute values, minus natural log of 1. Do you remember what natural log of 1 is? It's equal to 0. So you get 1/2 natural log of 10, which is approximately 1.151. I've got a series of examples on this slide just to help you quickly realize or recognize when it's appropriate to use the natural log integration. This denominator has a derivative of 3x squared plus 1, which is exactly the numerator. If that's the case, where the numerator is the derivative of the denominator, you can move exactly into natural log absolute value of the denominator plus c. Second example, secant squared over tangent. The derivative of tangent x is secant squared x dx. So that's derivative over original, And so that's a perfect candidate for natural log of the denominator, absolute value, because tangent can be 0 and it can be negative, plus c. The third one, we're pretty close. X squared plus 2x has a derivative of 2x plus 2. Almost there. So let's look over here. If I let the denominator be u, its derivative is 2x plus 2 dx. Divide both sides by 2, then x plus 1 dx can be replaced with 1/2 du, 1/2 du, and then we have 1 over the substitution. So that's 1/2 natural log absolute value of u plus c, and then since this is an indefinite integral, x squared plus 2x goes back in, and that is your general antiderivative. If you catch a fraction where the powers are equal, or if the power on top is larger, then you go back to the college algebra days of long division, and you take your denominator and long divide it into your numerator. X squared divided by x squared is 1. 1 times x squared plus 1 is x squared plus 1. Notice I skipped the x term in here because x squared plus 1 times 1 doesn't have an x term. It's x squared plus 1. Also remember from long division you have to subtract these and vertically combine like terms. X squared minus x squared is 0. X minus 0 is x. And 1 minus 1 is 0. X isn't large enough to divide by x squared, so this is where we stop. The long division, which means this original fraction is equal to 1 plus x over x squared plus 1. 1 over x, 1 plus x over x squared plus 1. This is equal, so instead of this fraction, we break it up. Now, I'm going to use a property of integrals and split this into the integral of 1 dx plus the integral of x over x squared plus 1 dx. The antiderivative of 1 is just x. This is the one where we got a little bit of work to do. The derivative of the denominator is 2x dx. We're missing a 2, so what I did was in red, I pinned in a 2, but I balanced it back out with a 1/2. And here's why. Because now I can do the antiderivative using natural log. 1/2 derivative over original means natural log of the denominator plus c. Since x squared plus 1 is always positive for all values of x, all real numbers of x, you can change these into parentheses. It's not wrong to leave them an absolute value, but if you know what's inside is never 0 or negative, then you can swap them out for parentheses. Let's check out a couple of integrals. Then we're going to use these later in the next unit when we start doing other types of integration. And this will be in Unit 2. These videos so far are just Unit 1. Let's look at the integral of tangent x dx. Recall from your quotient identities that tangent is sine over cosine. That allows us to rewrite tangent x as sine x over cosine x. Well, what's the derivative of cosine x? It's negative sine x dx. And I'm going to move the negative over. So now I've got du negative du, and this becomes 1 over u. Sine x dx becomes negative du, so that leaves 1 over the substitution. Well, that's negative natural log absolute value of u plus c, and sub u back in. Actually, that dx shouldn't be in there. I'm going to cross it out real quickly. That shouldn't be there. Okay. And then sub that back in, so you have negative natural log of cosine x in absolute values, because cosine can be negative, plus c. We're going to remember this for future use. The antiderivative of tangent x is negative natural log cosine x. Another one that we'll need to refer to later down the road in Unit 2 is the integral of secant x dx. Now, if I multiply something by 1, it keeps its value. Secant x plus tangent x divided by itself is just a really clever 1. Now, if I distribute through, that gives me secant squared x plus secant tangent over secant x plus tangent x, all dx. Well, it turns out that by multiplying by this clever 1, and that's all it is multiplying by 1, the derivative of tangent is secant squared. The derivative of secant is secant tangent. So by doing this, we've created a fraction where the denominator's derivative is the numerator. And I put that in red. If you take the derivative of your denominator, you get the numerator, which is perfect for our example because that just becomes 1 over u du. So our antiderivative is natural log absolute value of u, sub in the original, back in for u, and here's our general antiderivative. And then finally, let's do an definite integral using one of the problems from the previous slide. Let's calculate the integral from 0 to pi over 4 of square root 1 plus tangent squared x. From your Pythagorean identities and trig, let's recall that 1 plus tangent squared x is equal to secant squared x. That lets us replace and have square root of secant squared x, just using an identity. Square rooting a square gives us secant x, and from the previous slide, the antiderivative of secant x is natural log of secant x plus tangent x. It was actually the second example on the previous slide. Evaluated at our upper and lower integral limits, natural log of secant pi over 4 plus tangent pi over 4 minus natural log of secant 0 plus tangent 0. And that's from the fundamental theorem of calculus. Second one. Cosine of pi over 4 is square root of 2 over 2. So secant is the reciprocal of that. Tangent of pi over 4 is 1. Cosine of 0 is 1. Its reciprocal is still 1. And tangent of 0 is 0. Well, this totals out to 1, and natural log of 1 is 0. That eliminates the back half of the problem, which helps us. It simplifies it. If we were to rationalize multiplying both top and bottom by square root of 2, the 2's will cancel, and it just leaves a square root of 2. Plus 1. Natural log of square root of 2 plus 1 has an approximate value of 0.881. Remember in your online homework and test, if you're not asked to approximate, then be sure to use the exact value. I hope this video helps. Reach out if you have questions by email or phone, or come by the office and we'll work these out together. I am here to help, so reach out as needed. Thank you.